Welcome to the Smart Greenhouse series. In this video, I'll show you how to use deep learning models to predict both plant species and their health status using TensorFlow and Keras. We'll walk through three Python scripts, breaking down the steps involved in image augmentation, building models, and combining them for real-world predictions. If you're excited about using AI to monitor plant health, this video is for you. And don't worry, part two, where we'll focus on designing the circuit and coding for our smart greenhouse, uh, is coming soon. Stay tuned for that video. And in the meantime, let's dive into how AI can enhance your plant monitoring system. Before we dive into explaining the Python scripts, let me quickly walk you through my folder setup and how I organized the data. In the data folder, I have created separate subfolders for each plant species like mint, tomato, and cucumber. And within each of these folders, I've separated the images into their respective health status, healthy and unhealthy. This setup helps us train our deep learning models to recognize both species and their health conditions. For testing purposes, I started with just a few photos for each species and their health status, but I used an image augmentation script to increase the number of training images. This helps the model generalize better even with limited initial data. However, if you want your model to be more accurate, you'll need to add more photos for each species and health status. The more diverse your data set, the better the model will perform in real world scenarios. Now that you understand the data structure, let's dive into explaining the Python scripts and how they all come together to predict plant species and health status. In this image augmentation Python script, the goal is to increase the size of your dataset through image augmentation, which creates variation of existing images to help a machine learning model generalize better. Here is a simplified explanation. There's a directory setup. Right here, the script begins by defining the file path where your images are stored. It organizes them into different categories based on the species, for example, mint, tomato, cucumber, and their health status, healthy or unhealthy. Next, we have the image data generator. This is a powerful tool from TensorFlow's Keras library. It allows for real-time data augmentation where transformations like rotating, shifting, zooming, flipping, etc. are applied to images as they are being loaded into the model. This helps the model become more robust against variation in input images. Next, we have the augmentation function. Right here, this function, it loops over all images in each species health category. It reads, resizes, and prepares each images for augmentation. Using the image data generator, it generates multiple augmented images for each original one, in this case 30 different images, applying random transformations like rotating, shifting, zooming, and flipping. The augmented images are then saved in the same directory as the original image. Finally, the script calls the function to process all the species health combinations in your data set and outputs the augmented images, ensuring a large, more diverse set of data for training your machine learning model. The augmentation process helps the model learn better by making the data set larger and more varied without the need to manually collect more images. This increases the robustness and accuracy of the model in real world situations where the input data might vary in lighting, orientation, or size. The next script we're going to go over is the plant health model. This script is designed to build a deep learning model that classifies plant health, either healthy or unhealthy, based on images of plants. Um, the script first defines a function that goes through the data set organized into folders based on plant species and health status, for example, healthy or unhealthy. Um, it reads each image, resizes it to a consistent size, and stores it alongside its corresponding health labels, either 0 for healthy or 1 for unhealthy. Um, let's see. Next, the images are normalized right here, scaled down to make the model training process more efficient. This helps the neural network process pixel values between 0 and 1 instead of the original range 0 and 255. Next, let's see, the data set is then split into a training set and a testing set with 80% of the data used to train the model and 20% reserved for evaluating its performance. The split ensures the model is tested on data it hasn't seen before. Um, Next, we need to build the model. Uh, and the model's architecture consists of several convolutional layers which are great for extracting important features from images, followed by pooling layers to downsample the data. Um, After flattening the data, a dense layer with 128 neurons is added to learn more complex patterns. Finally, the output layer has two neurons since we're predicting two classes, healthy or unhealthy, and uses a softmax activation function to output probabilities for each classes. The models for training, the model is compiled with the Atom optimizer and a loss function suitable for classification. Uh, which computes the error between the predicted class and the true class. Um, the model is then trained for 10 epochs, meaning it goes through the training data 10 times to learn and adjust its weights. Um, and finally, once trained, the model is saved as .h5 file, so it can be reused later without needing to retrain it from scratch. The script also evaluates the model on the testing data, providing an accuracy score that indicates how well the model performs on unseen data. Overall, this script helps creates a robust health classification model using deep learning, making it easier to predict the health status of a plant based on an image. It takes advantage of convolutional neural network for processing image data, which are well suited for recognizing patterns and textures in images. The next script we're going to go over is the plant species model. This script is used to build a machine learning model that can classify the species of plants from images. In this case, it differentiates between mint, tomato, and cucumber. Um, the images needs to be loaded first. Um, so the data is organized by plant species and their health status. However, this script only focuses on identifying the species of the plant regardless of its health condition. It reads images from the subfolders and assigns species labels to each image. The species labels correspond to the index of the species in the list. In this case, mint is 0, tomatoes is 1, and cucumber is 2. Each image is resized, and both the image data and species labels are stored. Um, let's see, the architecture of the model is very similar to the health classification model, with convolutional layers for feature extractions and pooling layers to reduce the spatial dimensions of the data. The final layer has three neurons, one for each plant species. And the softmax activation function ensures the output is a probability distribution over the three species. Um, let's see, for training, the model is trained for 10 epochs using the Atom Optimizer and sparse categorical cross entropy uh, as the loss function, because we have multiple classes to classify. After training, the model is saved as a .h5 file for later use, and its accuracy is evaluated on the test set to check its performance on unseen data. The main difference in this script compared to the health model is the way the labels are assigned to species instead of health. And the numbers are output classes, 3 for species versus 2 for health. This script focuses on recognizing plant species from the image data while ignoring their health status. Next script we're going to go over is the script that runs both models. This script leverages two pre-trained models, one for plant species classification and another for plant health status classification. The goal is to predict both attributes for any given input image. Um, so the two models, plant species model.h5 and plant health model.h5s, are loaded at the beginning of the script. Uh, these models were trained and saved separately using the species and health classification scripts. By loading them both, the scripts can perform predictions for both plant species and plant health from the same image. Um, so the species labels, mint, tomato, cucumber, and health labels, health and unhealthy, are predefined. These are used to convert the model's numerical output back into human readable categories. Um, let's see. Before the model can make predictions, the input image must be pre-processed. The image is resized as this is the input size expected by the models. The pixel values are normalized, scaled between 0 and 1 to match the data format that the models were trained on. Let's see. For the prediction function, the predict species and health function is the core of this script. it takes the image path as input, pre-processes the image, and then runs it through both the species and health models. Uh, each model returns a probability distribution, and the highest probability is selected as the predicted class. The predicted plant species and health status are printed. Um, and finally, we have a function here, uh, right here. The script includes this sample called the predict species and health function, where you can pass the path to an image. The function will return the predicted species and health status for that image. The key takeaway from this script is its combined use of two separate models to analyze different attributes, species and health, from a single image. It demonstrates the practical application of both models in a single workflow, allowing for a more comprehensive analysis of plant data. So to run this series of scripts, here's the process you'll follow. First, you start by running the image augmentation.py script. This will augment the photos you have, uh, increasing the number of images by applying transformations. This step is crucial because it helps create a larger data set, which improves the training of our models. Next, you run the plant health model.py script to train the model for detecting the health status of the plants. After running this, you'll get the train.h5 file that stores the model for predicting plant health. After that, you run the plant species model.py script to train the species classification model, which will generate a separate .h5 file for predicting which species the plants belong to. Finally, after training both models, you run the run both models.py script. This will use two .h5 files created earlier to predict both the species and health status of a sample plant image. So now let's see that in action. I won't run the first three scripts again since I've already trained the models and generated the .h5 files, but let's run the run both models.py script to see the result. Here's our sample image. It's an image of a mint plant. It's in an unhealthy condition. Okay, we got the result, and as you can see, uh, the model successfully identifies the plant species and its health condition. The result matches our sample image, and the model works as expected. Also, additionally, I've included an API of a more complete model in the video description, which will be available in a week or two. This model provides much more information about the plant in an image, and you can upload your own images to try it out yourself. Um, Also, if you're following along and building your own smart greenhouse system, uh, I've also included affiliate links in the description for the components and tools I've used. Purchasing through these links helps support the channel at no additional cost to you. And that's it for today. I hope this video was helpful. If you found it useful, please give it a thumbs up. and don't forget to subscribe to the channel for more updates. Thank you for watching.